One of the most difficult things in electric circuits is determining whether resistors are in series or resistors are in parallel. I always see people make this mistake. Sometimes resistors are in series and people say that they're in parallel or vice versa. So in this video, I want to show you a way you can use to determine whether resistors are in series or they're in parallel, right? I have a few electric circuits here, I think around 4 or 5. So make sure you watch the video until the end so that you can see what I'm talking about. So let's look at this electric circuit on the right hand side, right? You can see here that we have a power source of 12 volts. And then we have one resistor of 2 ohms, right? Clearly, this resistor of 2 ohm is in series. Would you agree? But then the question is, why are we saying that this resistor is in series? I'm sure 99% of the people would definitely say that this resistor is in series. But the question is, why are we saying that it is in series? So we need to find a definition for a resistor in series so that we can base everything we're saying on a definition, right? So let's define what we mean when we say a resistor is in series. So as you can see now, I've written a definition for a resistor in series. When we say a resistor is in series, the resistor experiences total current, right? Because from our power source here, we have the positive terminal and the negative terminal, and then the current will flow anti-clockwise in this instance, right? From positive to negative. So there goes our current. It's flowing, and clearly on the 2 ohm resistor, there's no current splitting, right? So the 2 ohm resistor experiences I total, and then as a result we're saying that it is in series relative to the circuit, right? So keep that definition in mind. Every time when a resistor experiences total current, it is in series. Let me add another resistor in the circuit so that we can have more clarity. So now let's come back to our circuit. You can see that I've added this 3 ohm resistor here, right? So the question now I'm asking, is this 3 ohm resistor in series or in parallel? Let's stick to the definition. The definition says that if a resistor is in series, the resistor experiences total current. Clearly, the 3 ohm resistor is going to experience total current because there is no current splitting. So that 3 ohm resistor is in series relative to the circuit. Sticking to the definition, right? We're not guessing anything. We're not making an assumption. We are sticking to the definition. If a resistor experiences total current, then it is in series. Okay, as you can see here, I've added a 4 ohm resistor, right? The question is still the same. Is the resistor in series or in parallel? If we stick to the definition, there is no current that is splitting. So that 4 ohm resistor should be in series. And indeed it is. The 4 ohm resistor is in series. But then this is where I lose a lot of people. So let's look at the 2 ohm resistor and the 4 ohm resistor, right? Look at them. Is the 2 ohm resistor in parallel with the 4 ohm resistor? The 2 ohm resistor is not in parallel with the 4 ohm resistor. They are all in series because they are experiencing total current, right? In physics, we don't talk about parallel the same way we do in math, right? Because in math, when things are parallel, they are visually in parallel, right? But then in physics, you can see that this 2 ohm resistor and the 4 ohm resistor, they look visually in parallel to each other. But then in electric circuits, we're not talking about visually. We're talking about the current. Are they receiving total current or not? The 2 ohm resistor and the 4 ohm resistor are receiving total current. So they are in series relative to the circuit. They are not in parallel. So you can see that I've added the 5 ohm resistor, right? Now the first question we should ask ourselves, is the 5 ohm resistor in parallel with the 2 ohm resistor, right? Again, a lot of people would say that they're not in parallel to each other because they don't look parallel to each other. But then in physics, we're not talking about how they look. We're talking about the current, right? The 5 ohm resistor is indeed parallel to the 2 ohm resistor. Why are we saying so? Because as the current is flowing from the positive to the negative, right? When it reaches this point here, the current is going to split. A proportion of the current is going to go down this path, and then another proportion of the current will go down this path, right? So that means that the 2 ohm resistor is now parallel to the 5 ohm resistor, right? Because they're not experiencing total current. Is the 5 ohm resistor in parallel with the 3 ohm resistor? Yes, the 5 ohm resistor are in parallel with the 3 ohm resistor. They're not experiencing total current. Again, the 5 ohm resistor is in parallel with the 4 ohm resistor because they're not experiencing total current. But let's look at the 2 ohm resistor, the 3 ohm resistor, and the 4 ohm resistor, right? Those resistors on that path, are they parallel to each other, or are they series to each other? So that's where it gets a bit confusing, that the 2 ohm and the 3 ohm and the 4 ohm resistor, they're in series relative to each other. What do I mean when I say they're in series relative to each other and not relative to the circuit? I mean that we know fully well that RP is equals to 1 divided by R1 plus 1 divided by R2. So if we want to calculate the resistance in parallel for the circuit, I would say 1 divided by RP is equals to 1 divided by the 5 ohm resistor, right? Plus 1 divided by 2 plus 3 plus 4, the total resistance on that path. So what I do when I teach this session, I actually say that instead of 1 divided by R1, let's say 1 divided by RP is equals to 1 divided by the resistance on path 1 plus 1 divided by the resistance on path 2, right? Because here you can see that on this path, we add in the total resistance, right? We're saying 2 plus 3 plus 4, and then here it is, right? Because most people would say 1 divided by 5 plus 1 divided by 2 plus 1 divided by 3 plus 1 divided by 4, which is totally wrong, right? It's 1 divided by the total resistance on a path, plus 1 divided by the total resistance on the other path. So if you have 3 paths, like you're gonna see on the circuit we're going to do, you will also add the resistance on that path too. I think now our definitions are well defined and we can analyze electric circuits, right? So let's look at the left hand side. Let's look at the circuit here. So the first step you do, you determine the positive and the negative terminal, right? So in this circuit here for 11.1, this is the positive terminal and this is the negative terminal. The current flows from positive to negative, right? So it's going to flow in this manner. There we go, 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 and there we go. We're assuming that this switch is closed, right? So the question now is the 8 ohm resistor in series? Clearly, it is experiencing I total, so it is in series. Is the resistor X in series? It's experiencing I total, so it is in series. If you want to calculate the total resistance for this circuit, you're gonna say RT is equals to RS plus RP, but there's no resistors in parallel, right? So RP is going to be equals to 0. So we're gonna get RT is equals to RS plus 0 basically. But we know RS, we're talking about the resistance in series, right? And then for the resistance in series, you just simply add the individual resistors. So we're gonna have the 8 ohm plus X being our resistors in series, right? That's how you would analyze that circuit. But then it's pretty much straightforward. Let's move to the next one and see what happens. So let's move to this one here. Again, first step, let's identify the positive and the negative terminal, right? So here we have the positive and then here we have the negative. Assuming that the switch is closed, the current is gonna flow. There goes our current, there goes our current. And then keeps going, and then here at this point the current splits, right? So a proportion of the current goes down this road, and then a proportion of the current goes up that route. So clearly, this resistance in this path is in parallel with the resistance in this path, right? Because since the current is splitted, neither of the two paths are experiencing I total, right? So they're in parallel with each other. So if you want to calculate that effective resistance in parallel, we're going to say 1 divided by Rp is equals to 1 divided by R on path 1, right? Plus 1 divided by R on path 2. So let's look at path 1. On path 1, we have the 12 ohm and the 8 ohm, right? So that will be 1 divided by Rp being equals to 1 divided by 12 plus 8, and then plus R on path 2. But then on path 2, you can see here that the 16 ohm resistor is in parallel with the 4 ohm resistor, right? So separately, you have to calculate the effective resistance of that 2. And then after you've calculated the effective resistance of that 2, you can put it back in the equation to find that resistance. So what we can do, we can put it on the side and say that 1 divided by Rp will be equals to 1 divided by 16 plus 1 divided by 4, right? So Rp is going to be 1 divided by 16 plus 1 divided by 4 to the negative 1. Alright, so that's the effective resistance on this path. Now we can put it back in our equation and say 1 divided by 16 plus 1 divided by 4 to the minus 1. So here Rp is actually going to be equal to 2.76 ohms, right? That's how you would analyze the circuit. So let's move to the next one. And here we are. Let's look at our circuit, right? Again, we're identifying the positive and the negative, right? So maybe what you want to do, you'd want to pause the video and do it yourself and see if you can calculate the effective total resistance, right? Assuming that you did that, we have the positive here, and then here we have the negative. So the current is going to flow in this manner, right? If you're in grade 11, just forget about this. Just ignore it, right? Yeah, it doesn't, we're assuming that the switch is closed. That doesn't serve our purpose on this video, so let's just keep going. So in this part here, the current is going to split, right? So a proportion of the current is gonna go down this way, and then a proportion of the current is actually going to go down this way, right? So here already we can see that the 6 ohm resistor is not going to experience I total, right? So it is in parallel to something. It's in parallel to this 6 ohm resistor. But then not only is it parallel to that 6 ohm resistor, it's actually in parallel to the 6 ohm and the 2.4 ohm resistor, because this 2.4 ohm resistor is on the same path with the 6 ohm resistor, right? It's not individual resistors being parallel to each other. It's actually the paths that are parallel to each other. That's why we see that 1 divided by R on path 1 plus 1 divided by R on path 2, right? So before we go any further, if we want to calculate the total the resistance in parallel, we would say 1 divided by Rp is equals to, you know what it says, 1 divided by R on path 1 plus 1 divided by R on path 2. So here on path 1, we have 1 divided by the 6 ohm here, right? On the second path, we have this 2.4 ohm and this 6 ohm. So we're going to have 2.4 plus 6, right? So Rp is going to be 1 divided by 6 plus 1 divided by 8.4 to the minus 1, right? But then you can see that at this point here, the current quote unquote joins, right? So this resistor X here, it experiences I total. Based on the definitions we are proposing, it is in series relative to the circuit because it is experiencing I total. So here's our circuit diagram here. Again, this is the positive terminal, this is the negative. So the current is flowing anti-clockwise, right? Here we have a voltmeter, right? A voltmeter has very high resistance, so the current doesn't go there at all, right? So the current just keeps on flowing past the voltmeter, right? But then at this point, we have a resistor here. So the current is going to split, right? A proportion of the current is going to go down on this path, and then another proportion of the current will go down on this path. But then at this point here, the current rejoins, right? And then this ammeter A here is going to read I total. So now you can see that we have two resistor R, right? Let's say this is R1 and this is R2 for the sake of clarity. So R1 and R2 are in parallel to each other. They're not experiencing I total and they're on different paths. So if we want to calculate the total resistance in parallel for this second, we'd say 1 divided by RP is equals to 1 divided by R1 plus 1 divided by R2, right? There's so many electric circuits, I cannot do all of them, but I think I've done close to 10, 12 questions on electric circuits, past exam questions. So if you wanna check that out, there's a playlist on the channel. In the circuit represented below, the ammeters, connecting wires, and switch have negligible resistance, while the voltmeters have a very high resistance. X is a resistor with an unknown resistance. The battery has an EMF of 18 volts, while its internal resistance is unknown. And then it goes on to say that switch S is now closed. Ammeter A2 reads 0.3 amps, right? So here on A2, let's denote that we have 0.3 amps. And then it goes on to say that voltmeter V2 reads 6.8 volts. So let's go to voltmeter V2 and indicate that we're reading 6.8 what? 6.8 volts. And then 8.1 says define the term EMF of a battery. We know that the EMF of the battery is the maximum energy provided by a battery per unit charge passing through it, or is the work done per unit coulomb of charge, right? You can use one between those two definitions, it's allowed. And then 8.2 says calculate the reading on ammeter A1. So let's follow the current, right? This is the positive terminal and this is the negative terminal. The current flows from the positive to the negative. We are told that switch S is closed, right? So the current is flowing in this manner. So there goes our current, there goes our current. And then clearly here at A1, the ammeter we are interested in is total current, right? IT. So what 8.2 is asking us to do is to find IT. But then we cannot use EMF is equals to V external plus V internal because we don't know the internal resistance. But what we can do here with this 30 ohm resistor, right, we can find VP here. And then after we've found VP, we can then say that VP is equals to I multiplied by the 20 ohm resistor and find the current on this path, right? If we find the current on that path and we know the current on this path, then we can just add the two and they will be equals to IT. Why am I saying we're gonna add the two and they are equals to IT? Because at this point here, the current divides, but then even though it divides, it will still add up to IT, right? So let's go ahead and do that. So we can say that VP is equals to I multiplied by the resistance of the 30 ohm resistor. So what is the current on that path where we have A2? That is 0.3 multiplied by 30 ohm. So our VP will be equals to 9 volts, right? So now this is when we are using the 30 ohm resistor. Now we can pay our attention to the 20 ohm resistor. The 20 ohm resistor is in parallel, right, and is the only resistor there. So we'll also have VP being equals to I, let's just call this I2, right, the current on this path, multiplied by the resistance of the 20 ohm resistor. So the VP, we already said is 9. We're interested in I2, multiplied by 20, right? So we basically dividing both sides by 20, and if we do that, we get I2 is equals to 0.45 amps. So here on this path, on A2 we have 0.3 amps, and then on this path here we have 0.45 amps. So that will tell us IT, right, or the reading on A1 is equals to 0.3 plus 0.45, which is equals to 0.75 amps, right? And then we can move to 8.3. 8.3 says calculate the total external resistance of the circuit. So now that we have IT, right, we know the reading on V2 it is said to be equal to 6.8 volt, right? So now we can just say for the X resistor, V is equals to I multiplied by R. So what is the voltage there? The voltage is 6.8, and that is equals to the current, which is 0.75, because it is experiencing I total, right? And then multiply by X. So let's say resistance X here. So we're dividing both sides by 0.75. So we're gonna get that the resistance of X is equals to 6.8 divided by 0.75, which is equals to 9.06 ohm. But then that's not all we are asked to do. We are asked to find the total external resistance of the circuit, right? So clearly resistor X is in series, so now we can say that RS is equals to 9.06 ohm. Now what we can do is to find RP, the resistance in parallel, right? So we can say that 1 divided by RP is equals to 1 divided by R1 plus 1 divided by R2. So we're gonna have 1 divided by RP is equals to 1 divided by 20 plus 1 divided by 30. So RP will be equals to 1 divided by 20 plus 1 divided by 30 to the minus 1. If you put that in your calculator, you're gonna get 12 ohms. So now we can say that the total external resistance, right, will be equals to the resistance in parallel plus the resistance in series. So that will be equals to 12 plus 9.06, which will be equals to 21.06 ohms. And then we have determined the total external resistance of the circuit. Now we can move to 8.4. 8.4 says calculate the internal resistance of the battery, right? We have the EMF, we have IT, right? The total current, we have R external, we need small r, or the internal resistance, right? We know fully well that EMF is equals to the current multiplied by R external plus internal resistance, right? So we're basically gonna be solving for internal resistance here. So we're gonna have 18 being equals to the current, which is 0.75 multiplied by 21.06 plus R, right? So here what we can do, we can say that 18 divided by 0.75 is equals to 21.06 plus R. So 18 divided by 0.75 minus 21.06 is equals to R. So if you put that in your calculator, you're gonna find that R is actually equals to 2.93 amps. So there we have done 8.4, and now let's move to 8.5. 8.5 is saying resistor X is now replaced with another resistor of lower resistance, right? So we know that R external is equals to RS plus RP. So if RS is only the X resistor, and then now it is replaced with a lower resistance, then R external will go down, right? Let's carry on and read our Question: how will the reading on voltmeter V1 be affected by this change? Write down only increase, decrease, or remain the same. V1 is connected across our battery, right? But when the switch is closed, it's gonna read V external. So what happens to V external when we reduce the resistance on resistor X? The reading on V1 or V external will decrease. More on that on a second, because on 6.8.6 we are supposed to explain that, right? So let's talk about it. So we know fully well that EMF is equals to V external plus V internal, right? Sometimes it is called V lost. So let's talk about this. V external is I multiplied by R external, and then V internal is I multiplied by internal resistance. So we're saying that R external decreases, right? When R external decreases, I here goes up, right? This I here goes up, but the internal resistance remained the same, right? The internal resistance remained the same. So because the internal resistance remained the same, V internal increases, right? V internal increases. But we need EMF to still be constant, because EMF is a constant, right? So EMF is constant. Now you can see that if V external goes down, V internal should go up. If V internal go up, V external should go down. So here consequently, V external will decrease. So the question you might ask yourself is that, but I know fully well that V is equals to I multiplied by R. So since the resistance went down and the current went up, shouldn't V external stay the same? The thing is, even though the current is going up, right, it won't go up in such a way that V external will go up or remain the same. It will still go down because V internal is going up, and we need EMF to remain a constant. So 8.2 says that the circuit diagram below represents a combination of resistors in series and parallel. The battery has an EMF of 12 volts and an unknown internal resistance R. And before 8.2.1, we are told that when switch S is open, right, here's switch S here, the reading on the ammeter, so we have some I, which is equals to 1.5 amps, right? And then 8.2.1 says let's calculate the total resistance of the circuit, right? We have internal resistance, so we cannot just use V is equals to I multiplied by R, right? We have to use EMF is equals to the current multiplied by the external resistance plus the internal resistance. The question says let's find the total resistance of the circuit. So we're looking for R external plus internal resistance, right? We have the EMF, it is given to us, and then we have the current, right? It should be obvious what we're gonna do now. So we're going to have 12 being equals to the current 1.5 multiplied by R external plus internal resistance. So we divide in both sides by 1.5, right? So we get R external plus internal resistance being equals to 12 divided by 1.5, which is equals to 8 ohms, right? So R external plus the internal resistance is equals to 8 ohms, and that's the total resistance of our circuit. And then 8.2.2 says let's determine the internal resistance of the battery, right? We know now that R external plus the internal resistance is equals to 8 ohms. So if we can determine R external, then we're going to be able to find R internal. But how can we determine R external? We know fully well that R external is equals to the resistance in series plus the resistance in parallel, right? So now let's actually analyze our circuit. So we have a positive terminal here and we have a negative terminal here, and then the current is flowing from the positive to the negative, right? And then at this point here, there won't be any current splitted, right? Because the switch is open. So the current just keeps on flowing, keeps on flowing, keeps on flowing, keeps on flowing. So basically what we have here is two resistors that are in series relative to the circuit, right? So R external will be equals to 3 plus 4, and then we're seeing that we don't have any resistors in parallel, right? So we're gonna have 0 here, and then that will just be equals to 7 ohms. So now we can say 7 plus the internal resistance is equals to 8. We're substituting R external into this equation here. So the internal resistance will be equals to 8 minus 7, which is 1 ohms, right? So the internal resistance is 1 ohms, and now we can do 8.2.3. 8.2.3 says let's determine the energy dissipated by the 3 ohm resistor in 3 minutes, right? So in order to determine the energy, so we know that the power is equals to the work divided by the change in time, right? So the work is equals to the power multiplied by the change in time. Every time when the question says let's find the energy dissipated, we're looking for the work, right? But then the power can take different forms. The power is equals to I squared multiplied by R. The power is equals to V squared divided by R. The power is equals to V multiplied by I. So depending on the variables you have, right, you use one of these equations to find the power. Clearly, for the 3 ohm resistor, we have the resistance, right, which is 3 ohm, and then we have the current, right? From the current, we can calculate the voltage, right, and then use the other equations, but there's no need. So what we're gonna do here, we're gonna use this equation here, because we have the variables that allows us to do so. So now the work is going to be equals to the power. In place of the power, we're going to have 1.5 for the current, right, squared multiplied by the resistance, which is 3 multiplied by the change in time, 3 minutes. But we know in physics we talk about seconds, right, not minutes. So we're going to have 3 multiplied by 60. There's 60 seconds in a minute, and then if you punch that in your calculator, you're gonna get 1215 joules, and that is the energy dissipated on that 3 ohm resistor. And now let's do 8.3. 8.3 says switch S is now closed, right? Let's go ahead and close switch S. So here's switch S here, right? And we're closing it. When we close switch S, now the current is going to split here, right, at this point. So we're going to have a proportion of the current going in this direction, and then another proportion of the current going in that direction, right? And then how will each of the following be affected? Write down only increase, decrease, or remain the same. 8.3.1, the total resistance of the circuit. The total resistance of the circuit will decrease, right? Why am I saying so? Because if the current splits here, right, then the 2 ohm resistor and the 3 ohm resistor are now in parallel with each other. So R external will actually be equals to R in series plus the resistance in parallel, right? So this is going to be 4 ohms plus, now the 3 and the 2 ohms are in parallel with each other. So we're going to have 2 multiplied by 3 divided by 2 plus 3, and that is equals to 5.2 ohms. Clearly, this is less than the R external we had initially, right? That R external we had initially was 7 ohms. So if we close that switch, the total resistance of the circuit will go down. And 8.3.2 says, how will the reading on ammeter A be affected? If V is equals to I multiplied by R, right? And we're saying that the resistance went down then the current should go up, right? So the reading on the ammeter will increase. If you decrease the resistance, the current goes up. And now let's do last but not least 8.4. 8.4 is saying a conducting wire of negligible resistance is now connected between points X and Y. Before we read any further, let's just go ahead and connect X and Y. So here's X, and then let's connect X to Y, right? And then it goes on to say, as shown on the diagram above, what effect will this have on the temperature of the battery? Write down only increase, decrease, or they stay the same. What effect will this have on the temperature of the battery? So if we connect X and Y, right, we have reduced the resistance. Yeah, because now the only resistor that will be getting current is the 4 ohm, right? So we have reduced the resistance. What we can see first is that R external decreases, right? So R external will decrease. But then what is the consequence of R external decreasing? If R external decreases, then IT, the total current in the circuit, increases. If the total current increases, and we know that V internal is equals to IT multiplied by small r, right? We're saying that the current increases, the internal resistance is the same, so V internal increases, right? If V internal increases, the work done by the battery will increase, and as a consequence, the temperature will also increase. We have a battery in a circuit which has an EMF of 12 volts and an unknown internal resistance R. And then we are told to ignore the resistance of the connecting wires and the ammeter. And then 8.1.1 says write down the reading on voltmeter V1, right? So we are told that switch S is open. Let's see what switch S being open implies, right? So here's switch S here, that is open. When this switch is open, no current is flowing to all the external resistors, right? So as a consequence, the voltmeter V1 is gonna read the EMF of the battery, which is 12 volts. But then realize something, we're not saying that when a switch is open, a voltmeter across the battery will read the EMF. That's not what we're saying. If the switch is open such that all the other external resistors don't get any current, then it's gonna read the EMF. So for instance, let me show you something. Let's say the switch was somewhere here, right? Let's say this is where the switch was located. If the switch was here, then this 6 ohm resistor that I'm circling will not get any current, right? The current will just come to this 6 ohm resistor, come back to this 2.4, and then it will just pass here. It won't come here. So we'd still have those other external resistors getting current, and the voltmeter that is connected across the battery won't read the EMF. So the voltmeter is reading the EMF because all external resistors are not getting any current. And then for 8.1.2, we are supposed to write down the reading on voltmeter V2. We've already said that all the external resistors are not getting current. So the reading on voltmeter V2 will be V2 equals to I multiplied by R. What is I? We said that they're not getting any current, so I will be 0. Multiplied by R, that will just be 0 volt. And then for 8.2, we are told that the switch S is now closed, and then we're given the reading on the ammeter, which is said to be 1.2 amps, and we are told that the power dissipated in resistor X is 5.76 watts. And then 8.2 says define the term power. That is pretty much easy and straightforward, right? Power is the rate at which work is done. Power is the rate at which work is done. The formula says so too, because you know that power is equals to the work divided by the time. So it's just the rate at which work is done. And then now we can move to 8.3. 8.3 says calculate the resistance of resistor X. What information do we have about resistor X? So for resistor X, we know that the power dissipated is equals to 5.76 watts, right? And then we know that the current at resistor X will be equals to 1.2 amps. So why are we saying that the current at resistor X is 1.2 amps? That is because the current is the same everywhere in a circuit, right? It just divides in parallel resistors, but then apart from that, the current is the same everywhere else in the circuit. So if you want to find the resistance, we can say that so we have a resistance which we don't know, right? So if we relate those three terms, we can say that the power is equals to the current squared multiplied by the resistance. This is the formula we have in electric circuits, right? And then so we're gonna have 5.76, which is equals to 1.2 squared multiplied by R. So we're just gonna have R equals to 5.76 divided by 1.2 squared, which is equals to 4 ohms. So now we have the resistance of resistor X. Now let's move to 8.4, which says calculate the total resistance of the circuit. So we know that resistance total is equals to the sum of the resistance in series plus the sum of the resistance in parallel. What is the resistance in series? There's only one resistor in series, right? Which is this resistor X here, which we said that is 4 ohms, right? So we can say our resistor in series has a value of 4 ohm. Now we're supposed to calculate the resistance in parallel, right? So when the current is flowing, it's flowing, and then it's gonna split at this point, right? A proportion of the current will go that direction, and then a proportion of the current will go this direction. So this 6 ohm resistor here is in parallel with these 2 resistors here, because the current split, and then it comes to these 6 ohm resistors, and then another proportion comes to these 2 resistors. So this 2.4 ohm resistors is in parallel with this 6 ohm resistor, which is not so obvious to many people, but that is the case. So now we can say the resistance in parallel. So usually people want to do it like this: 1 divided by resistance in parallel equals to 1 divided by resistor 1 plus 1 divided by resistor 2, and so on. So we're gonna have 1 divided by the resistance in parallel is equals to 1 divided by 6, right? Being this one here, and then plus 1 divided by 6 plus 2.4, because these 2 resistors are in parallel with this 6 ohm resistor here. So we're gonna have 1 divided by resistors in parallel is equals to 1 divided by 6 plus 1 divided by 8.4. So if you put this in your calculator and you solve for resistance in parallel, you get the resistance in parallel to be equals to 3.5 ohms. So now we can say that the resistance in total will be equals to 3.5 ohms plus 4 ohms, right? This is the resistance in parallel, and then this is the resistance in series, which will just be equals to 7.5 ohms, right? Yeah, nothing complicated up to so far. And then 8.5 says calculate the reading on voltmeter V2. So let me just erase some of the things I've put here so that we can try to determine the reading on voltmeter V2. So we need the potential difference as a consequence of this 6 ohm resistor here. So what we know about parallel resistors is that the current split, right? So this section will have a certain proportion of the current, Ix, let's say, and then this path will also have a proportion of the current, let's say Iy, right? But then another thing we know is that the voltage is the same, right? The voltage that goes this side in this path is the voltage that goes in this path, right? That's what we know about parallel resistors. So if we can determine the voltage that goes in this path and the voltage that goes in this path, which are the same, then we can then be able to calculate the current in these two paths, right? And from the current, we can then determine the voltage difference as the potential difference as a consequence of these 6 ohm resistors. So what I'm saying is that let's find voltage parallel, and from this voltage parallel, we're going to be able to find the current which goes in this path that is the 6 ohm resistor, and then from that current we're going to be able to find V2, right? So let's see what that leads us. So we have Vp which is equals to the current in total multiplied by the resistance in parallel, right? So this will be equals to 1.2 because the current is said to be 1.2, right? So it will be 1.2 multiplied by 3.5. Why are we multiplying by 3.5? Because the resistance in parallel is 3.5, and then this will give you 4.2 volts. So now we can calculate the current that goes down in this path. So we can say that this current is equals to the voltage divided by the resistance, right? What is the voltage? The voltage is the same on both paths, and we have said that is 4.2 volts. And then the resistance, now the resistance is not 3.5, but is rather 6 plus 2.4, right? Because we only want the current, the proportion of the current that goes down in that direction. So that will be 4.2 divided by 8.4, which is equals to 0.5. So now that we have the current that will flow through this 6 ohm resistor and this 2.4 ohm resistor, we can then find the potential difference that is being picked up by the voltmeter 2, right? So we're gonna say voltmeter 2 will give us a reading of the current multiplied by the resistance, obviously. So that will be 0.5 multiplied by 6 ohms, which is 3 volts. So this V2 here will read 3 volts. Now what you can think about is what will the reading if we connect, let's say we connect a voltmeter here, let's call it V3. What will be the reading on V3? Please, can you please solve the problem, and then you can drop your answer in the comment section, and I'm gonna tell you if it's correct or not. What will be the reading on voltmeter 3?